1,200 rounds per minute. That's the sound American infantry heard tearing across North African sand in 1942. A sound like ripping fabric, only faster, louder, deadlier. The MG42, Hitler's Buzzsaw. By early 1943, U.S. ordnance had formally evaluated a captured MG42. By late 1943, the Army ordered 30 06 conversions, and 2 prototypes finally reached Aberdeen in January 1944. One fired a single shot at Aberdeen Proving Ground and stopped. The other managed 1,583 rounds before choking on 51 malfunctions. Firing was discontinued in February 1944. The program was effectively abandoned by March. American engineers copied everything about the German design except one invisible detail. A detail that measured roughly 1/4 of an inch. That quarter-inch difference turned the most feared weapon of World War II into a jam-prone failure. February 1943. U.S. Ordnance authorities published their first formal report on a captured MG42. The findings are undeniable. Quick barrel changes without tools, belt feed system that never jams, stamped steel construction, cheaper and faster to manufacture than anything America produces. 1,200 rounds per minute cyclic rate. American soldiers initially ridiculed the weapon's stamped metal parts. Then they realized how much faster and cheaper guns of this type could be manufactured. Then they faced it in combat. The MG42 dominated battlefields where it appeared: North Africa, Sicily, Italy, later France, Belgium, Germany itself. Wherever German infantry dug in, that distinctive tearing sound followed. American troops gave it names: Hitler's Buzzsaw, Hitler's Zipper. The British called it Spandau, an old generic term for German machine guns dating back to World War I. German soldiers had their own names: Hitlersäge, Knochensäge, the Bone Saw. Soviets called it the Linoleum Ripper. The sound was unmistakable. A bar gunner squeezed off careful bursts at 450 rounds per minute. The M1919 fired 400 to 600. The MG42 spit 1,200. Some models pushed 1,500. The math was devastating. Allied infantrymen learned to wait for the brief pause caused by belt and barrel changes before advancing. That pause was all they got. German crews swapped barrels in seconds, no tools required, and resumed fire. Sustained suppressive fire that pinned entire platoons. After engagements, American officers examined captured German weapons. The MG42 stood out, not precision-machined like American designs, stamped from sheet metal, spot-welded, riveted, yet superior in nearly every measurable way. The MG42's development began in February 1937, when the German Army Ordnance Office requested designs for a stamped universal machine gun easier to manufacture and with higher rate of fire than the MG34. 3 companies submitted proposals: Metall- und Lackierwarenfabrik Johannes Großfuß of Döbeln, Rheinmetall Borsig of Sömmerda, and Stübgen of Erfurt. Großfuß AG's entry proved the best design by far, employing a unique recoil-operated roller locking mechanism. The company had no earlier experience in weapons manufacture, specializing in pressed and stamped steel components. Their staple product was sheet metal lanterns. Dr. Werner Gruner, one of the leading design engineers with Großfuß, knew nothing about machine guns when given the task, although he specialized in the technology of mass production. Gruner attended an Army machine gunner's course to familiarize himself with the characteristics and sought input from soldiers. He then recycled an existing Mauser-developed operating system and incorporated features from his experiences with Army machine gunners and lessons learned during early stages of the war. Two stamped steel halves welded together, a recoil-operated roller locking system, a muzzle booster capturing expanding gases to cycle the action, quick change barrel, belt feed, adjustable fire rate, every component designed for mass production and battlefield reliability. The roller locking mechanism was the heart. As the bolt moved forward, cylindrical rollers pushed outward into recessed tracks in the barrel extension, locking solid during firing. Upon discharge, barrel and bolt recoiled together 7 millimeters. Then angled surfaces allowed the rollers to cam inward, unlocking the bolt. The bolt continued rearward, extracting and ejecting the spent case. The barrel snapped forward. The cycle repeated. 1,200 times per minute, more than 20 rounds every second. Human ears couldn't distinguish individual shots, just continuous tearing noise. Initial trials of the Gross-Fuss functional model presented in April 1938 gave rise to improvement requests. The resulting Gross-Fuss MG39 prototype gun, presented in February 1939, remained similar to the earlier MG34 overall. A limited run of about 1,500 improved MG39/41 pre-production models was completed in 1941 and tested in combat trials by year's end. In early 1942, the final model was officially accepted. Manufacturing of the mass production model began as the MG42, contracts going to Gross-Fuss, Mauser-Werke, Gustloff-Werke, Steyr, others. The weapon was first deployed in May 1942 by the Afrika Korps and introduced by mid-year on all fronts. Production during the war amounted to over 400,000 units. 17,915 in 1942, 116,725 in 1943, 211,806 in 1944, 61,877 in 1945. By 1943, MG42 production surpassed MG34 production and continued until war's end. The U.S. Army wanted to manufacture this weapon. It was technically advanced, much easier to make than existing American light and medium machine guns, intended as a replacement for both the Browning automatic rifle and the M1919A4. Throughout 1943, evaluation of captured MG42s continued. The War Department eventually issued directives: reverse engineer the MG42. Adapt it for .306 Springfield ammunition. Test it. If successful, mass produce it. Saginaw Steering Gear Division of General Motors received the contract, an automotive manufacturer, not a firearms specialist. They were already swamped with other wartime production: M1 carbines, aircraft components, artillery parts. The T-24 conversion became a side project. Engineers measured every dimension of captured MG42s, photographed every feature, analyzed the roller locking mechanism, documented the belt feed system. They retained the basic design: stamped steel construction, three-handle configuration, roller locking bolt, recoil operation, belt feed, quick change barrel compatible with the M2 tripod used by the M1919. What they changed: the barrel, chambered for .306 Springfield instead of 7.92 times 57 mm Mauser. The bolt, massively increased from 17.8 ounces to 47 ounces, nearly 3 times heavier. Stiffer return spring. The goal: reduce cyclic rate to something consistent with U.S. doctrinal requirements. The German 7.92 times 57 Mauser cartridge and the American .306 Springfield were roughly comparable in power. both full-power rifle rounds. The German used a heavier, larger diameter bullet. The American round pushed its lighter bullet slightly faster. Power wasn't the issue. What Saginaw steering gear didn't adequately adjust, the mechanism's dimensional tolerances for the longer cartridge. The 7.92 times 57, Mauser has an overall cartridge length of 3.228 inches. The .306 Springfield measures 3.34 inches, roughly 1/4 inch longer. That quarter inch would prove catastrophic. January 1944. Aberdeen Proving Ground. 2 T-24 prototypes arrive for testing. Test engineers load a belt of .306 ammunition into the first prototype. They charge the weapon. The roller mechanism engages. An engineer pulls the trigger. The gun fires one shot. Stops. The bolt failed to eject the spent cartridge. Jammed solid. A second attempt produces identical results. One shot, one jam, one failure. The second prototype performs marginally better. It fires intermittent bursts before succumbing to ejection failures and feeding malfunctions. When it runs, the cyclic rate averages 614 rounds per minute. Half what the German original achieved, barely faster than existing American weapons. Over the next month, evaluators attempt every possible fix. They substitute parts, change extractors, modify feed mechanisms, adjust springs, replace bolts. Nothing produces reliable automatic function. From January to February 1944, testing at Aberdeen Proving Ground proves unsatisfactory. Firings are discontinued in February 1944 after 51 malfunctions across only 1,583 rounds by authorization of Major C. Belison, Office of the Chief of Ordnance, when it becomes evident the weapon requires further development. In March 1944, the U.S. military reaches its conclusion. Functioning of the T-24 machine gun prototype is unsatisfactory. Further development required before subjecting the weapon to standard testing procedures. The realization, the .306 Springfield cartridge is too long for the gun's mechanism to easily and reliably work with. The program is effectively abandoned. Saginaw steering gear never gets the opportunity to correct the flaws before World War II ends. What went wrong? The MG42's roller locking mechanism was engineered with extreme precision for the German cartridge dimensions. Bolt travel, roller engagement timing, extraction sequence, ejection dynamics, everything calibrated for a cartridge of specific length. When American engineers chambered the weapon for .306, they lengthened the chamber to accommodate the longer case. What they didn't do, proportionally adjust the bolt's rearward travel distance to match the dimensional increase. The longer cartridge meant the bolt didn't travel far enough rearward to reliably extract and eject spent cases. The timing was wrong. Extraction was incomplete. Ejection was inconsistent or absent entirely. The roller locking system demanded precise timing. As bolt and barrel recoiled together, the rollers had to cam inward at exactly the right moment to unlock the action. With the longer cartridge occupying more space in the chamber, that timing shifted by fractions of a millimeter and fractions of a second. In a weapon cycling 1,200 times per minute, 20 rounds per second, those fractions were everything. The heavier bolt compounded the problems. The original MG42 used a 17.8-ounce bolt because that mass, combined with the spring rate and recoil impulse of the 7.92 Mauser cartridge, produced optimal cycling speed and reliability. The T-24's 47-ounce bolt, installed specifically to reduce fire rate, disrupted the entire system's mechanical harmony. The weapon's recoil dynamics, extraction timing, and bolt velocity were no longer synchronized. The failure wasn't a single cause. It was cascading mechanical problems stemming from dimensional incompatibility, improper bolt travel, altered timing, and disrupted extraction geometry, all triggered by that quarter-inch difference in cartridge length. American engineers assumed they could simply swap cartridges without fundamentally redesigning the mechanism. They assumed the longer case wouldn't matter. They assumed close enough was good enough. They were wrong. While the T-24 failed at Aberdeen, German MG42s continued dominating every theater: Normandy, the Ardennes, the drive into Germany. The weapon proved exceptionally reliable across diverse conditions: mud, sand, snow, rain, extreme temperatures. The design's roller locking system, when properly matched to its intended cartridge, performed with remarkable consistency. American infantry still carried bars and M1919s. Adequate weapons, reliable weapons, but not MG42s, not 1,200 rounds per minute, not quick barrel changes without tools, not the psychological impact of that sustained, tearing roar. When Allied forces captured German supply dumps, MG42s were valuable finds. While soldiers couldn't regularly use captured German machine guns due to ammunition compatibility and logistics concerns, the weapon's reputation was undeniable. The irony: Germany's most effective infantry weapon was cheaper and faster to produce than American alternatives. It outclassed every Allied squad weapon. Multiple working examples existed. Detailed technical documentation was available. Yet American engineers couldn't successfully copy it. Not because the design was too complex, because they underestimated how much 1/4 inch mattered. The T-24 failure had consequences beyond 1944. The lessons influenced American machine gun development for decades. In the 1950s, the U.S. developed the M60 machine gun. Soldiers called it the Pig. The M60 borrowed the MG42's belt feed mechanism and incorporated elements from the German FG42's gas operation. But it was designed from the ground up around 7.6 2x 51mm NATO, not adapted from an existing mechanism built for different ammunition. The M60 had problems: chronic parts breakage, heavy weight, difficult barrel changes requiring an asbestos mitt, but at least it functioned. The MG42 lineage continued. After the war, West Germany rechambered the design for 7.62 NATO, creating the MG1, then MG2, then MG3. The MG3 remains in service today, 80 years after the original design. Yugoslavia manufactured the M53, nearly identical. Austria produced the MG74. Italy adopted variations. The German design, when properly engineered for its cartridge, required no fundamental changes. 90 years later, MG42 derivatives still serve worldwide. The T-24 prototypes disappeared into history. One survives in museums, a reminder that visible features mean nothing without invisible precision. This is what happens when form is copied without understanding function, when engineers assume dimensional differences don't matter, when close enough replaces exactly right. The MG42 wasn't just stamped steel parts and a roller locking bolt. It was an integrated system where cartridge dimensions, chamber length, bolt travel, roller timing, extraction dynamics, and ejection sequence worked in perfect mechanical harmony. Change one variable, even by 1/4 inch, without compensating for cascading effects throughout the system, and the entire mechanism fails. Saginaw steering gear focused on what they could see: the roller mechanism, the stamped construction, the belt feed. They missed what they couldn't: the precise dimensional relationships and timing sequences that made everything work together. 1/4 of an inch. That's all it took to turn Hitler's buzzsaw into a single-shot failure. Engineering isn't about copying shapes. It's about understanding why every dimension exists, what purpose it serves, how changing one element cascades through the entire system. The Germans understood. They spent years testing and refining from 1937 through 1942. They ensured every dimension was correct, every tolerance tight, every interaction validated under extreme conditions before mass production. American engineers, under wartime pressure and occupied with other priorities, tried to shortcut that process. They paid the price in catastrophic failures and an abandoned program. Today, the MG42 remains one of history's most influential weapons. Its descendants serve in militaries worldwide. Its roller-locking system influenced countless designs. Its stamped construction revolutionized manufacturing philosophy. Its rate of fire set standards that still apply. The T-24 exists as a footnote, an example of what not to do, a reminder that invisible details determine success or failure. American soldiers in North Africa, Italy, France, and Germany heard that tearing fabric sound and knew what it meant: 1,200 rounds per minute. Sustained fire that could pin entire units. A weapon that proved devastatingly effective in combat. The War Department ordered copies. General Motors built prototypes. Aberdeen tested them. One fired a single shot and jammed. The other managed 51 malfunctions in 1,583 rounds. All because American engineers changed a barrel to fit a cartridge roughly 1/4 inch longer than the German original and didn't properly adjust the bolt travel, extraction timing, and mechanical geometry to match. Sometimes the most critical engineering details are the ones you can't see. Sometimes 1/4 inch is the difference between the most feared weapon of World War II and an expensive failure that can't fire reliably. The MG42 proved it on every battlefield. The T-24 proved it at Aberdeen Proving Ground. If stories like this, where invisible engineering details determined the outcome of weapons, battles, and wars, interest you, hit that like button and subscribe to the channel. Next time, we're covering another piece of World War II technology where one overlooked detail changed everything.